Hello and welcome to section 2.1 on derivatives. In this section, we will incorporate limits into our concepts from section 1.4. If you need a review on 1.4, now is an excellent time to rewatch that video. With the application of limits, averages become instantaneous and secant lines converge to tangent lines. This video will conclude with the definition of a derivative. An important concept in calculus, the derivative and its applications will be the focus of chapters 2 and 3. As we'll soon discover, tangent lines are fundamental to the concept of derivatives. The tangent line to a curve at a point is the line that best approximates the curve near that point. But what does this definition mean? The graph of f of x doesn't look much like a line, but if we zoom in near P, say to an x range 0.2 wide, it begins to straighten out. But if we zoom in again, say to an x range 0.02 wide, the curve on this range almost appears to be a line. In fact, if we continue to zoom in, then this curve would continue to straighten out. The line that is appearing is our tangent line at P. Remember, the tangent line is the best approximation of the curve P. If we zoom back out to an x range 0.2 wide, and if we zoom back to our original magnification, then we see how the tangent line and the curve separate the farther they are from P. This is because the tangent line is approximating f only near P. We have a definition, but how can we find a tangent line? We'll do this by combining sections 1.4 on secants and section 1.5 on limits. Recall that a line passing through 2 points on a curve is a secant line. The closer a point Q is to P, the better our secant line approximates the curve near P. The further Q is from P, the worse the resulting secant line approximates the curve. With this in mind, to visualize a tangent line at P, we take the limit of secant lines for P and a point Q as the point Q is drawn nearer and nearer and nearer to P. We can now visualize a tangent line, but how does that help us find an equation representing the tangent line at P? To answer this question, we will use the limit of secant lines as Q approaches P. Recall from section 1.4 that a secant line between the points Q and P has a slope that is an average rate of change. As the tangent line at x equals a is found by taking the limit of secant lines between x equals a and x equals b while b is drawn towards a, the slope of the tangent line is the limit of the slope of the secant lines as b approaches a. Therefore, the slope of the tangent line at a is the limit of the average rate of change for f between a and b as b approaches a. Since the tangent line passes through the point a, fa, once you know the slope of the tangent line, you can use the point slope equation to write the tangent line. The slope of the tangent line is very important. The slope of the secant line is the average rate of change between 2 points, but a tangent line is the limit of those 2 points being drawn together. Therefore, the slope of a tangent line can almost be thought of as the average rate of change for a single point, but it is no longer an average, it is now instantaneous. It is important to keep in mind that when we apply limits, secants become tangents and averages become instantaneous. Recall from 1.4 that s is a function reserved for the distance an object moves with respect to time. The average velocity of an object between 2 times is the average rate of change on s. Similarly, the instantaneous velocity of an object at a certain time is the instantaneous rate of change for s. When we take limits, averages become instantaneous. As promised in the introduction, we conclude section 2.1 by defining the derivative of a function. Derivatives will often be denoted by f prime, and the derivative of a function f at the point x equals a is the instantaneous rate of change of f at x equals a. That is, the derivative is the slope of the tangent line. Often we will use an alternative but equivalent formula for the derivative of a function at a point. Rather than taking the limit of secant lines from x equals a to x equals b with b approaching a, we can replace b with the value a plus h, where h is the distance between the values a and b. As b approaches a, the distance between them, h, will approach 0. For example, Let's take the derivative of f equals the square root of x at the value a equals 16. Using the first equation for a derivative in blue and the second equation in green, we have two limits which look different but are equal to the same value, f prime of 16, the derivative of f at 16. If you are nervous because you are not sure of how to calculate these limits, don't worry. In section 1.6, we'll learn how to calculate limits from equations. To sum up 2.1, with limits, average rates of change become the instantaneous rate of change, a value representing the derivative at a point and the slope of the tangent line. Now that you know the basics, be sure to strengthen your understanding through practice.